Okay, now we move on to talk about the normal cumulative density function. So the green is the PDF, and to obtain the red, we basically integrate the area under the green curve at specific points, and then we divide that area by the total area. And you already know it will be zero at the extreme left point. At the extreme right point, you are looking at the total area under the green curve divided by the total area, right? And that will be 100%. And that's why it goes from 0 to 100%. The important point is that for any given small xi, right, any given point, say 10, you're looking at the area under the curve to the left. So to the left of the x equals 10, it will be this area here, and then you divide it by the total area. And this middle point here, which is about 12, the area will be half, right? It will be 50% because you're looking at the middle point on the CDF. I mean, we're looking at normal CDF for, CDF for normal distribution. So it will be, it's symmetrical. So it will be half or 50% at this point. So it's important to realize that percentiles are different from P10. This P10, P50, P90 are probabilities that we use in reserves evaluation in petroleum engineering. So they are different from percentiles, right? So you all are familiar with percentiles. Like, well, the 90th percentile will correspond to a relatively high value, right? So if you're looking at percentiles on a test where the maximum score is 100%, the 90th percentile will correspond to about 90% on the total score, right? It's not going to correspond to 5 out of 100 or something. Those are the lower percentiles. But for the P10, P50, P90, it's actually like the opposite. It's essentially 1 minus these percentiles. Why is that? It's the way the probabilities are defined, which is what I show here. So for the percentiles, you're looking at the probability that the random variable is less than or equal to an xi. What is an xi? Any value on the x-axis. So xi could correspond to 12, which is the 50th percentile. So you're looking at the probability that the reserves is 12 or less for the 50th percentile, right? Because the area is always the area to the left for the percentiles. Another way the question can be framed is, what's the probability that a random variable is at most xi, at most 12? So at most means it's xi or less. Whereas these P10, P50, P90 is written the other way. Its probability it's greater than or equal to xi. So you are looking at the area to the right divided by the total area. You see the difference? And that's why it's 1 minus this, right? The probability that x is greater than or equal to xi is equal to 1 minus probability that capital X is less than or equal to xi. So if the question is asking you for P10, P50, P90, you're looking at probability that the random variable is at least xi. I hope that's clear. Now we move on to talk about log normal probability distribution. We have talked about normal distribution, right? So we also have log normal distribution. And in log normal distribution, it just means that the random variable x, if you take the log, the natural logarithm of the random variable x, and then you plot it on the x-axis and you have frequencies on the y-axis, then the distribution will be normally distributed. You see that? So in normal distribution, you just plotted the frequencies against the random variable x on the x-axis. If instead of the random variable x on the x-axis, you plot the natural logarithm of the random variable x on the x-axis, and then it's normally distributed, what you have is a log normal probability distribution. So that's what I explained here, that the variable x has a log normal distribution if log x, natural logarithm of x, is normally distributed. Very important to note, in most programming languages, when you use log x, you're actually asking for natural logarithm. If you want log to base 10, then you have to type log 10x in most programming languages. So that's the difference. It's the log of x that is normally distributed. But typically we will plot against the x itself, and that's why you'll see the distributions are usually skewed to the left or to the right, which we had talked about previously. From the central limit theory, if a variable is the product of two or more independent and identical distributions, IID, it will be log normally distributed. So if you have a normal distribution, another normal distribution, and you take the product, well, that product will be log normally distributed. Whereas if you take the sum, it will be what? Normally distributed. That's what we talked about on the normal distribution. The probability density function is given in this form. It's similar to the PDF for normal distribution, but the important difference is this. So it's the ln of x, the natural logarithm of x, that you put in here. Whereas in normal distribution, this was x, and then this x wasn't there. So you don't have to memorize this, you just need to realize that the function, this PDF, has a mathematical expression, and that's what is implemented in those packages that we are using precisely in NumPy. This equation can be integrated numerically to obtain the CDF as we did for normal distribution, and it's the CDF we typically use in probabilistic modeling. Probabilistic, stochastic, they mean the same thing. So we use the CDFs. Why? Because the y-axis goes from 0 to 100%, and they correspond to probabilities. Mu and lambda for this distribution is not just the mean of x, it's the mean of the natural logarithm of x, which is why we are subtracting it out from natural log of x. So this mu, or log normal distribution, it's the mean of the natural logarithm of x. How about sigma? It's the standard deviation of the natural logarithm of x. So mu and sigma are respectively mean and standard deviation of the natural log of x.